Okay, here we go then with another section from the moles topic. As you can see, no longer in my kitchen. We're also using a new piece of software, so we'll see how it goes. Might need to make some changes as we go along, but we'll see if it works out. This session is all about reacting masses and volumes. There's the statements from the course guide, and really we're going to be looking at using these to solve some calculation questions. But before we start, we need to check we understand what's meant by an ideal gas. Now, it's a hypothetical situation. Particles don't occupy any space, right? So we're assuming that they're not taking up any space in the container itself. We're also assuming that there's no interactions, so there's no intermolecular forces. And for that to occur, to be ideal, we're going to have a low pressure and a high temperature, because these are conditions that kind of keep the particles apart, if you like. So gases are most ideal, most closely follow these laws that we're going to meet in a little while, at low pressure and high temperature. So these are some gas laws that you'll be working on in class. Boyle's law: pressure is inversely proportional to volume. So what's causing the pressure here is these particles hitting the walls of the container. If you make the container smaller, hopefully you can understand they're going to hit it more often, so the pressure is going to go up. This relationship is important in your body. If you let the diaphragm go down, volume increases here, which means the pressure decreases, which means air rushes in and your lungs fill with air. Charles' law: relationship between volume and temperature, important for hot air balloons. Heat the gas up, it expands, right? And as a result, its density decreases and the hot air balloon goes up. Hopefully no one in class has been heating sealed containers, because obviously that's going to explode over time. There's this law here: pressure relating to temperature. If you increase the temperature, the particles have more energy, they move around more, they collide with the container more, pressure builds up, and eventually that can's going to go pop. And the last one, Avogadro's law: of volume is proportional to the number of moles. And so if we have more moles of gas, then we would expect to see a larger volume. And we'll look at some calculations to do with that shortly. Right, so let's take some of those laws, put them into the combined gas law, and you can have a look here. We've got two sets of conditions. First set of conditions, second set of conditions. So it's the same amount of gas, just being exposed to different pressure, volumes, or temperatures. Now, as long as the pressure agrees in terms of its units on both sides, volume agrees with these volume units, that's fine. So you're always working in centimeters cubed, or you're always working in pascals. The only thing to watch out for is that your temperature must be in Kelvin. And you can pause me and have a look at this worked example down there. The ideal gas law: PV equals nRT. P, again, pressure; V, volume; N, number of moles; R, gas constant, 8.31, and T is again in Kelvin. And it's worth spending a moment thinking about what these units need to be. So this again has to be in Kelvin. It must be in Kelvin. This is always going to be 8.31. This is a number of moles, volume, and pressure. Now, if pressure is in kilopascals, or it may be in pascals, they're your options. If we're using kilopascals for the pressure, then we need to use decimeters cubed for the volume. If we're using pascals for the pressure, then we work in meters cubed for the volume. Maybe you can see that going from this to this is like multiplying by 1,000. But going from this to this is like dividing by 1,000. This is kind of like a scaling thing. So you either work with this pair or this pair. Just be careful, be consistent. Pressure is exerted by 3.2 grams of oxygen in volume of light. So we don't know P. We do know the volume. It's in decimeters cubed. So my answer is likely to come out in kilopascals. So PV is equal to N, the number of moles, which is going to be 3.2 divided by 32. Because oxygen is, of course, O2. So that gives us the number of moles. PV equals N times R times T. T again needs to be in Kelvin, plus 70. I'm rather lazy, I've done 273.15. And if I solve that for P, my pressure comes out to be 95.01 kilopascals. Right, here's an application of using that law. Again, making use of this PV equals nRT equation. So we've got our pressure, 101 kilopascals. So if we're working in kilopascals, I need to be working here in decimeters cubed. So PV 820, so converting centimeters cubed to decimeters cubed, I divide by 1000, because 1000 centimeters cubed in a decimeter cubed, is equal to N, which I don't know yet, times R times T. If I solve that for N, it's 0.0321 moles, which means that that's equal to my mass, which I've been told in the question, divided by my molecular mass, and I can solve that for my molecular mass. It comes out to be 46.7 grams. So it's a way of identifying what molecule or compound you might be working with in a question. Now, we spent a bit of time looking at reacting masses style questions in other units. So we've got our 3 steps: convert to moles, look at the mole ratio, come out of moles. We can do the same thing here again. If we use a piece of information that at room temperature and pressure 1 mole of any gas equals 24 decimeters cubed. And there's another relationship that at standard temperature and pressure 1 mole of any gas is 22.4 decimeters cubed. So this question is assuming room temperature. So if we've got 2.4 grams of magnesium, again we can do our reacting masses style question. Firstly, convert that to moles, so it's 2.4 divided by 24, which means I've got 0.1 moles. The second step, look at my equation. Well, 2 moles of that react with 1 mole of that. So that tells me how many moles of oxygen I'm dealing with. Now if I know that 1 mole of a gas is 24, that 0.05 is going to be 120 centimeters cubed. Right, now there's a slight shortcut that we can employ. So rather, as we saw on this slide, rather than having to do all these coming in and out of moles with this 24 decimeters cubed, if everything's in the gas phase, we can just work with the volumes. And we can just use it as a ratio of those volumes. So pause me and have a look at that slide. Talk a little bit about this. If we're interested in moles of gases, obviously gas laws are important for this. You might be designing airbags for a car. This is trinitrotoluene, TNT, an explosive which will rapidly produce a large volume of gas, hence its explosive force. So you can do calculations, as you've seen previously, to help support research into these. Okay, let's have a look at some more practice. 3 questions here. Pause me, have a go at them, and then you can look through my answers, which I'm going to do now. So this is an Avogadro's law question. You can see everything's in the gas phase, so we can just use our volume relationships. Now it says 10 centimeters cubed of methane is burned in this. Assume it's 20% oxygen, so 20% of that means there would be 30 centimeters cubed. So in terms of finding a limiting reactant, 10 of this, because it's a 1:2 ratio, would need 20 of oxygen. And I've clearly got more than 20. So this is my limiting reactant. It's going to determine how much products I make. So in terms of how much CO2 I'm going to get, well, it's a 1:1 mole ratio, so I'm going to end up with 10 centimeters cubed of that. What volume will be occupied by that much nitrogen? Right, so this is a PV equals nRT question. PV equals nRT. So our pressure, 1.12 times 10 to the 5 times volume, don't know. Number of moles, we can work out, because number of moles is mass divided by mass of 1 mole times R times T. And if we solve that for the V, it comes out to be 1.90 times 10 to the minus 4 meters cubed. So if we look, we're working with pascals, which means my answer is going to be in meters cubed. So if I multiply that by 1000, I get decimeters cubed, and I can also multiply that by another 1000 to get it into centimeters cubed. I prefer working in that, which means I have 190 centimeters cubed. Right, last question. 1 decimeter cubed cell Lagrange. So this is a combined gas law question. It's a different colour. So P1, V1, so the initial set of conditions, it's at 1 atmosphere, the volume is 1, temperature must be in Kelvin, so that's going to be 298, is equal to second set of conditions. We don't know the new volume, the pressure still 1, and the new temperature is going to be 303. And if I solve that for the new volume, the answer comes out to be 1.02 deciliters cubed. Right, so recap of things that you should have picked up from this. There's the resources that we used. Thank you for listening.